So we were in medias res here. So this is the result that we found for the matrix element in SCET. And as I said, this at this level is still a bare operator. And we need to renormalize this operator in the same way we renormalize anything else in the quantum field theory. So basically, you are used to the renormalization of the fields and the coupling constants in the Lagrangian. But if I give you an external operator composed of fields, a so-called composite operator, so for instance, a 4-fermion operator in weak interactions, typically, even though you have already renormalized the fields, composite operators built out of fields. In almost all cases, they require additional U renormalization. And we see that this is the case here because we didn't get a finite result. Okay? Now, I told you that you couldn't think of these poles as UV poles. One thing you learn in your QFT classes is that the coefficients of ultraviolet poles do not depend on infrared regulators because they describe the short distance property of the theory. This seems to be violated here because you see that there are collinear logs, ultrasoft logs, they all depend on the off-shellness of the quarks. So it looks like even though these are ultraviolet divergences, they care about the infrared regulators that you choose. That would be bad, of course. But things are nice because if you add up the three terms here, you see that the p squares cancel out. We have a log 1 over p square here. We have a minus log 1 over p square here. So the p1 square cancels, the p2 cancels. And really, when you analyze the structure here, the poles that we get are 2 over epsilon squared plus 2 over epsilon log mu square over q square plus 3 over epsilon. Okay, so this is free of infrared regulators. As it has to be, but again, it's non-trivial. It's this thing that we needed correlated scales in SCT. I told you to factorize double logs, we need 3 correlated scales. And yes, we have the ultrasoft scale and the collinear, they're infrared scales, but they are related in this seesaw type relation to the hard scale. So if you have, 2 powers of this divided by this, you get q square, and that's what's happening here. So in order to renormalize this operator, we will need to apply a counter term, a renormalization factor of this form. It depends on the high scale q square. That's still unusual, but that actually is characteristic of Sudakov problems. So whenever there's a Sudakov problem, you will find this logarithmic dependence of renormalization factors on the hard scale, but not on the infrared regulators. Okay, so we're going to introduce a renormalized SCET current. So I won't write it out over and over again. This was the bare operator. Let me call this V mu SCET, or better would be 2-jet. It's a 2-jet current. And this was the bare operator, okay? And now I'm going to write an equation that, while there's always 2 ways of writing renormalization conditions, one is to say that we start with the bare operators and we write them as a renormalization factor times the renormalized operator. Okay, and in doing this, basically we introduce the scale mu. in some sense, actually the matrix element of the Baire operator doesn't depend on mu. It doesn't look like this. There's mu's all over the place. But actually remember that there's also an alpha mu here. And in the Baire theory, this alpha S mu is proportional to mu to the minus 2 epsilon. And if you take this mu to the minus 2 epsilon and you combine it with these poles, you would find that all the mu's actually disappear. This expression, even though it doesn't look like it, the mu dependence between alpha and these mu's completely cancels out. So this is mu independent. It's only the subtraction of the poles which will turn this into a mu dependent expression. And you can either write Baire is C times renormalized, or renormalized is inverse C times Baire. This way of writing it is nice because all the poles must go here. So you can directly read off the expression for the C factor by knowing the poles in the Baire matrix element. Okay? So in this way we get, and remember the C factor only absorbs the poles, nothing else. So here we get now CF alpha S over 4 pi, 2 over epsilon squared plus 2 over epsilon log mu square over q square plus 3 over 3 over epsilon. That's in the MS bar scheme. That's the MS bar renormalization factor plus terms of order alpha squared. Important result. Oh, forget about the log of 4 pi and Euler gammas. Yeah, in the MS bar, you don't have these. Yes. It depends on how you define epsilon. Is it really confusing? Sometimes you see log of 4 pi's and Euler gammas, but then you redefine mu in such a way that they are absorbed, and then you get this expression in the MS bar scheme. Good. Now, this is the C factor, and this is defined such that the remaining terms which are finite define this renormalized matrix element. So we can now write down the renormalized matrix element of the renormalized current. Oh, sorry, mu is the Lorentz index and mu is also the renormalization scale. Well, I think you can tell the difference. And at one loop, I mean, strictly speaking, we should take this result and divide by this expression, but at one loop, this simply subtracts these pole terms. So the first line here is gone and the second line remains, okay? So this is U bar N bar P2, gamma mu perp, U N P1, and now times 1 plus CF alpha over 4 pi. And what's left now is log square mu square over P1 square plus log square mu square over P2 square minus log square mu square Q square over P1 square P2 square plus 3/2 log mu square over P1 square plus mu square log mu square over P2 square plus 8 minus my constant C from the wave function normalization minus 5 pi square over 6. So now we have a finite answer, okay? But as we will see, this expression is much more useful than just removing the poles. We'll see in a moment. Oh, sorry, and I forgot the Wilson coefficient, CV of Q squared. This is the SCET answer after renormalization for the Sudakov form factor. Now, how do we derive an expression for CV of Q square? Well, obviously by matching, okay? In the same way that we have discussed before. So here we have computed the Sudakov form factor in SCET. So if this is my Sudakov form factor, one way to derive it is to say this is CV of Q square in mu times sort of the SCET matrix element of this two-jet current operator in SCET. So this is an SCET calculation. But of course, at the same time, this needs to be equal to the Sudakov form factor in QCD. So we could now repeat the calculation of the Sudakov form factor in QCD. I had given you the results in the toy model where I ignored the numerator structure, but you can also do the calculation without ignoring numerator structure. And then what you find is something like this. Minus 2 log Q square over P1 square log Q square over P2 square plus 3/2 log Q square over P1 square plus log Q square over P2 square minus 2 pi square cubed minus C, also the wave function renormalization, the same wave function renormalization entering there. What we had in the toy model is this double log. What we didn't have in the toy model was the single logs. Okay, they come from the numerator structure, and the constant was different. And now what we do is we match these two. Okay, we set them equal. If we did things right, the dependence on little p square, the dependence on P1 and P2 square should be the same in this expression and this expression. And the difference should be, if we did everything right, the difference should be such that it defines a function of only Q square. And that should be this function. And this actually works. This actually works. If you compare these two expressions, you get CV of Q square and mu is equal to 1 plus CF alpha S over 4 pi. And now what remains here is minus log square Q square over mu square plus 3 log Q square over mu square minus 8 plus pi square over 6. And it's really only depends on Q square. And, you know, this is exactly what many lectures ago, 2 days ago, we got from the region analysis when we worked out the hard region, except we worked in the toy model. So we would not get this single log, but we got the double log in the toy model, and the constants are maybe also a bit different. Okay. This is a very famous result. I think Anish derived this in some paper. We also derived it in some paper. Later, we also computed the two-loop corrections to this result. It's very important because it's a very fundamental object. It's the current, okay, the quark current. There's a quark current, a gluon current. Those are the simplest external operators. And we have these results for both of them. So you see how this is all interconnected with the method of regions that motivated us from the start, but the philosophy now is different. Now in SCT, we get all these low energy contributions. We can renormalize this operator. Here's the renormalization factor. Then the matrix elements are finite, and then the matching that we need to make this result equal to the full QCD result is a finite hard matching coefficient, which only depends on the hard scale, as it should be. I didn't understand the question. What is the renormalization condition? Well, in MS bar, the condition is that the C factor should only remove the pole terms. You can have other renormalization schemes. For instance, you should, I don't know, you could have a different renormalization scheme where you know, sometimes you could say at a certain value of Q squared, this renormalized current should take a certain value or whatever. You could do that. But in MS bar, all you do is to remove the poles, nothing else. It's a scheme. It's not unique. So basically, the freedom that you have is to add a constant here and subtract a constant there. You could shift constants between. So one scheme to the other is adding a constant in the C factor and removing it there. And then, of course, so basically you shift the constant between here and here. So that would be the scheme freedom that you have. Okay. Okay, so now some fun RT evolution equations. If you go back to this construction which we had here, we have these three scales. They're all very different. Logs of any ratio of scales will produce a large log. Okay. Now, the goals in the EFT is to factorize these scales. We have only halfway accomplished that. We factorized the hard scale from the rest. We still have to do this factorization, second half of the lecture. But you know, you also at a practical level, you would also like to resum these logs. Because let's say the scale ratio is 10 or 50 or whatever. You have alpha log squared. That is easily bigger than 1. Okay, and so if you want to trust your perturbation theory, you should resum these logs. Normally people say you should even resum single logs. That's also true, but it's even more true for double logs because the log is simply much bigger in that case. And to do the resummation, we need renormalization group equations, and we'll study it now for this coefficient mu. For instance, at the moment we have computed this at fixed mu. Now we want to lower mu. We want to move this scale down as long as we stay in the perturbative region, and in that way we sum all the large logarithms in this hard matching coefficient. You see it here. If mu is of order the hard scale, all these logs are small, and you can compute this. This is what you call your initial condition. But now you want to evolve mu down from the hard scale to lower scales, and then you get large logs in these expressions, which you need to resum. And this is what we want to do now. If we have this equation, in more complicated situations, there could be more than one operator with the same quantum numbers. If I have two operators or more, this C factor becomes a 2 by 2 matrix or 3 by 3 matrix. You have to generalize what I'm telling you now to matrix notation, but the structure is the same. I will just, in this particular case, there's a single operator. And the RG equation then is of that form, d by d log mu, or mu d by d mu of the two-jet current. Let me call this alpha so you don't get confused. Is an anomalous dimension, and for the operators, one usually defines a minus sign in the RG equation. It's an anomalous dimension, which I will call capital gamma sub v. It will also depend on Q square times the two-jet current itself. And you can show that and you can, for instance, look in my Lissouche lectures in 1901 06573. Let me advertise this school. This was a Lissouche school on effective field theories. Anish was also one of the lecturers. And this was a 4-week school. So I think the proceedings of this are on archive, and you can find a lot of really detailed sets of lecture notes on all these things and many more. It went up to EFTs in cosmology and inflation and gravitational waves. Anyway, you can find the following equation derived, that the anomalous dimension to all orders in perturbation theory can be obtained by taking a derivative with respect to the running coupling, alpha s, of the coefficient of the 1 over epsilon pole terms in the renormalization factor. So this is the coefficient of the 1 over epsilon single pole. But to all orders in alpha, this is true. Not just one loop. You see that already at one loop, where is it? The C factor has a double pole and single poles. At 2 loop, you get quadruple pole, triple pole, double pole, single pole, and so on and so forth. The statement is you only need the single pole. Take the single pole in the C factor, take a derivative with respect to alpha, and multiply by alpha, and you get the anomalous dimension. At one loop, this is easy to do. We only need these 2 terms. Taking a derivative and adding alpha back at one loop has no effect, but there is a prefactor -2. So basically, we get -2 times the coefficient of the 1 over epsilon pole, which in our case means, and this is true for any anomalous dimension, not just for this one. This is true for any anomalous dimension. So what you find is CF alpha, now not over 4 pi, just over a single pi without the 4, and then log mu square over q square plus 3 halves. This anomalous dimension is known to 3 loop and computed in some of our papers, actually. Now, when you learn field theory, advanced field theory, renormalization of composite operators, normally you learn that in perturbation theory there are logarithmic corrections which can become large and that you can resum them with the help of anomalous dimensions, and the anomalous dimensions are normally just numbers like the beta function. A conventional anomalous dimension is just alpha over pi plus alpha over pi squared with some coefficients. Here we see a logarithm in an anomalous dimension, and that's very unusual. Yeah, if you wish, yeah, didn't you see this is a matrix? Now, if you wish, just read this as a matrix equation. If you have n operators, this is a vector of operators. This is a vector of operators. This is an n by n matrix. This is an n by n matrix. This relation is still true. Yes, but in this particular example, there is only a single operator. In other examples, the best known example is weak interactions, the 4 fermion theory. So there, for instance, if you have a 4-quark operator, you have to add color indices to the 4 quarks. And there's 2 ways of doing that. You can have, the first 2 quarks the same color and the second pair of quarks the same color, or you can have the first anti-quark and the 4th quark the same color and the intermediate ones the same color. So there's always 2 color structures. So in this case, you have at least, you have a 2x2 system, 2 operators which under gluon exchange, they change color and they mix into each other. And then simply this becomes a 2x2 matrix, this becomes a 2x2 matrix, this relation is still true. Again, not more complicated, but not more difficult conceptually, but more complicated technically, because you'll have to do with matrices, but formalism is exactly the same. This, however, is a new feature. We have a single log in the anomalous dimension. You could vary, because I want to use this anomalous dimension to start at a high scale and evolve this thing down to a low scale. Then this logarithm becomes large. Okay, if it would happen that at 2-loop order I get an alpha log square here in the anomalous dimension, that would be really bad, because then this series for the anomalous dimension itself would not converge. It would be spoiled by large logs. That doesn't happen. That doesn't happen. So the fact that there's a log here has to do with the fact that we deal with Sudakov problems. In a Sudakov problem, the typical structure is, tree level 1 loop alpha log squared, 2 loop alpha squared log to the 4, and so on, okay? And we want to sum all of these double logs, and in order to sum a series of double logs, you need an anomalous dimension with a single log, but one can prove because clearly, when you take d by d log mu of such a series, you can take a derivative of a double log, you still end up with a single log. So something like that needs to happen. But one can prove that gamma v contains only a single log to all orders in alpha. So in other words, gamma v of q square and mu to all orders, I can write in the following way. It is a single log with a coefficient, don't be surprised, that one calls the cusp anomalous dimension. Remember the second lecture in HQET times log mu square over q square plus a quantity which is called little gamma v, which is just a function of alpha. So this is true to all orders in alpha strong. So this single log is not just there at 1 loop order, it's there at n loop order, just a single log. And that's why this anomalous dimension is useful. This log can become large, but going here from 2 loop to 3 loop to 4 loop, nevertheless, terms get smaller and smaller and smaller. So it's not that the perturbative series doesn't converge. There's a large factor here in front of this term, but the perturbative expansion means the next loop correction is much smaller than the previous loop correction, simply because here and here we have a regular alpha S expansion just with numerical coefficients. And at the end of today's lecture, I'll come back to Wilson loop origin of this result, basically. So, great. This is an important result. Come back to that in a little while. Now, we have our result, basically the form factor, the Sudakov form factor, was now a function C of Q square and mu, and the matrix element of this current, 2jet current of mu, okay? And of course, this scale mu, we introduced, like always, to separate, to factorize things in what we call short distance and long distance. Long distance is in the EFT, short distance is integrated out, okay? But obviously, if we change mu up or down, it just means that we are redistributing contributions from the Wilson coefficients to the matrix elements. The physics should be invariant, right? So if I change mu a little bit, I put a bit more in the matrix element and I take it out from the coefficient, or vice versa. So the physics should be independent. So in other words, you know, mu by d mu of the product C of Q square and mu and V 2jet of mu must be 0 in order for physics to be invariant of mu. And since I have a renormalization group equation, this is, by the way, this is what we call renormalization group equations. Anything that has a d by d mu on the left-hand side is a renormalization group equation. If I have the renormalization group equation for V, and I have this equation, I can directly derive the renormalization group equation for my hard matching coefficient. Mu d by d mu of CV of Q square and mu is, well, what is it? Obviously, it satisfies the same equation, but with a plus sign, right? Then when the derivative acts here, I get plus something times C, and when it acts here, I get minus the same something, and then it cancels out, and we get 0. So we get this result with a plus sign. And using also this result, yeah, sorry, I was almost confused. So minus, so we get this with a plus sign. In other words, we get this anomalous dimension, so we get gamma cusp of alpha s times log mu squared over Q squared plus little gamma e of alpha s times C of Q squared and mu. This is not difficult, but this is now the RG evolution equation for the hard matching coefficient. And solving this equation, so the philosophy is we have this expression, we evaluate this at Q square, mu square equal to Q square, then it doesn't have any logs. We can trust this result. It's a convergent perturbative expansion, no large logs. So we start there, and then we solve this equation, and we can evolve down as far as we want, however, always staying above the scale lambda QCD. So things are under control, right? We can read off expressions for the cusp anomalous dimension. So gamma cusp of alpha. Comparing this with this, you see gamma cusp is simply CF alpha S over pi. At one loop order plus order alpha strong squared. And the little gamma, comparing this with this, the little gamma is minus 3/2. So minus 3 CF alpha S over 2 pi plus order alpha S. Do you know what CF is? CF is 4/3. No, it's NC squared minus 1 over 2 NC, which is 4/3. The Casimir eigenvalue of the Casimir operator in the fundamental. representation. So these are the one loop results. The cusp anomalous dimension now is known to 4 loops. And this anomalous dimension is known to 3 loops. So people work quite a bit in getting very high accuracy. And the reason is that this is relevant for Drell-Yan production at the LHC, which is the most precise collider process ever observed. And that's why people want to really push the theory so that it can keep up with the phenomenology. I forgot when we started. Was it 3 o'clock? Yeah, okay. How do you solve such an equation? So the solution, it's actually not difficult to solve this equation, even though it looks very complicated. Any idea how I solve such an equation? I mean, if I have a derivative of a function, is some other function times the function itself? Yeah, we can take the logarithm basically. We can divide by CV on the other side, and we get d by d mu of log c is just this thing. And then the solution is just the integral over that side, and then we exponentiate. So the general solution is CV of q square and mu is equal to CV of q square and let me say mu h, where mu h is the initial condition. Normally, we choose mu h of order q. Whether it's equal to q or 2 times q or 1/2 times q is up to you, but it should be of order q so that at that scale, these logarithms are small or absent even. The most natural choice is to set it to q, and then there are no logs. That's the starting value. So here, perturbation theory is fine. And now times an exponential, and the exponential is the integral over scales, d mu prime from mu h to some lower scale mu. And now simply whatever is written there, gamma cusp of alpha s of mu prime log mu prime squared over q squared plus gamma v of alpha s of mu prime. And that's the general solution. And one easy way out would be that you take these expressions now, or you work in higher loop order. You take these expressions and you do this integral numerically. It's nowadays completely straightforward, of course. You need a implementation for the running coupling alpha of mu, and then you can simply do this integral numerically. You can also work it out analytically by changing variables from mu to alpha of mu, and then write this as an integral over running couplings with these expressions of the running couplings. I posted a new homework. The first problem is to derive the SCET Lagrangian with a mass term. Very easy, but very instructive. The second problem is to work out this solution by switching variables from mu to alpha of mu. So you go from mu to alpha of mu as a new integration variable and use the fact that d alpha, d log mu is the beta function of alpha s, beta function of QCD, and then this becomes an integral over alpha s, and you can solve it perturbatively. Good. So far on this, I don't want to dwell anymore on the details of the solution, straightforward from here. Much more important, and really the last thing we should do before stopping is to discuss the interactions of collinear fields with ultrasoft gluons. And this will be completely familiar to you from our HQET discussion. So this is called the decoupling of ultrasoft gluons. And you'll see that it proceeds in exactly the same way as our discussion of HQET and the decoupling of soft gluons from the heavy quark. Remember the key fact at leading order in the effective Lagrangian, I mean, there was an interaction between collinear and ultrasoft fields. That interaction was the only thing that had a lambda expansion. That was the only thing that had a leading term and a subleading term and so on and so forth. And at leading order, there was a single interaction of a collinear, of an ultrasoft gluon to a collinear quark. And that interaction was like this. We had the collinear derivative here. Let me write it out. Then this is n dot a collinear of x. And now we have the coupling to the ultrasoft gluon. Similar structure, except that here we needed to perform an expansion, a multipole expansion. So this is at x minus, yeah, multipole expansion. Okay, and we keep only this single component because what enters here is the small component of the collinear gluon field. And the ultrasoft gluon field has the same scaling as far as the n dot a component is concerned. Okay, so this is why the ultrasoft gluon was a leading interaction. And there is an x minus because of the multipole expansion. Now, in HQET, we learned that whenever the gluon interaction to a field comes through a 4-vector rather than gamma mu, comes through a 4-vector, it was V mu in the case of HQET, we can remove it by a soft Wilson line. Okay? And so this coupling can be removed by filter definitions. By a filter definition. And the filter definition is like in HQET. The original field psi n goes over to a soft Wilson line. Now in the n direction, not in the v direction. This is a light-like Wilson line now, not a time-like Wilson line. And because the field here sits at x minus, it will only be a Wilson line depending on x minus, not the full x. And then we have a new field. And the new field, we'll see in a moment, does not interact anymore with the ultrasoft particle. Now, we also have a collinear gluon here. So I also need to tell you what happens to the collinear gluon. The collinear gluon transforms to Sn x minus times the new collinear gluon times Sn dagger x minus. The gluon transforms in the adjoint, not in the fundamental, so I need to, it has transformations from both sides because it is itself an n by n matrix. And the SCET Lagrangian also contained the Wilson line, W of x, the collinear Wilson line, and the collinear Wilson line also transforms from the left and the right. And what is the soft Wilson line now? I always end up the last few minutes of the lecture running from left to right and back all the time. But this is in the nature of this. So the next building you build, you do it round, and you have the blackboard all around, and then by the time we come back, the lecture is over. Okay. No, joke aside, this is the most amazing blackboard I've ever seen. So this should be enough. Maybe. So what's the soft Wilson line? Completely analogous to what we had. Sn of x is equal to path ordered exponential IGS integral minus infinity to 0 dt n dot a ultrasoft of x plus nt. And now it's n, not n bar. For the collinear Wilson line, we needed n bar. For the soft Wilson line, we need n. It's analogous to HQET. In HQET, the particles move along the velocity direction, and the Wilson line is along the velocity direction. The collinear particles move along the n direction, and the soft Wilson line is along the n direction. The collinear Wilson lines were strange. They were in the opposite direction. But that's because n bar dot p was the large component. But this is the right definition of the soft Wilson line. And now we have the usual magic that n dot t plus gs n dot a ultrasoft x minus acting on Sn x minus. That's the ultrasoft covariant derivative acting on the soft Wilson line. It destroys the soft Wilson line, but if we write it as a differential operator that acts also on anything else, then we simply get this result, right? Same relation we had written many, many times. So this follows from I n dot d ultrasoft Sn equal to 0. And now I start my walking back and forth. If you look here now, if I pull out from this field a Wilson line, then this term and this term acting on the Wilson line will just give this term. Okay? So when I move the Wilson line through here, so it cancels the Wilson line from here, I get rid of this term. But the collinear terms stay there. So let me write it out in detail. So it then follows that Cn x n slash over 2 I n dot d plus gs n dot a collinear x plus gs a n dot a ultrasoft x minus times Cn. Written in terms of the new field, I get Cn0 of x n bar slash over 2. I get from here an Sn dagger x minus. Here I get an Sn. When I move this Sn through the derivative, okay, this term disappears. So I get the Sn x minus, and now only the collinear piece. times Cn0 of x. And notice the collinear gluon also got Sn S dagger from the left and the right, so I get the Sn here also for this term, and the Sn dagger cancels the S from the collinear field. These two things cancel each other because S is unitary, and this is just the ordinary collinear derivative. So I get the redefined collinear field, the collinear derivative in terms of the redefined gluon field, and the redefined quark field again, and I forgot the n bar slash over 2. And this is again a free Lagrangian. No, it's not a free Lagrangian, but there's no coupling anymore to the ultrasoft gluon field. So there's no coupling to ultrasoft gluons anymore. Now, in the case of HQET, it was even more shocking because we removed all the gluon interactions. In this case, there are still gluon interaction. In fact, you know, this is just the collinear interactions are all still there. So these quarks, these collinear quarks interact with collinear gluons, perfectly fine, nothing lost there, but they don't interact with ultrasoft gluons anymore. And this is true also for all other terms in the Lagrangian, also in the Young-Mills sector. You will find that the same field redefinition removes all these interactions. And the reason is that they always come in this form. Okay? Now, in HQET, we have already said this is not so shocking. It's really like choosing a particular gauge. And you know, at the end of the day, physics is gauge invariant. So if you remove these couplings here, they will reappear somewhere else, and they reappeared in the form of external operators, right? And it's the same thing here. Nevertheless, in the context of SCT, it's very, very useful to be able to have this decoupling at the Lagrangian level, because in terms of the new fields now, my SCET Lagrangian looks like this, with no interactions between the blobs. Inside the blobs, yes. Inside the blobs, we have all the QCD interactions, but no interactions between two blobs. So this is now the SCET after decoupling. Okay? And you'll see in a moment why this is so incredibly useful. So this ultrasoft decoupling is really the key to proving what's called factorization. Factorization means that at the level of cross sections or decay amplitudes, we are able to take an amplitude and really factorize it in a multiplicative sense into something that depends only on collinear fields, something that depends only on anticollinear fields, and something that depends only on ultrasoft fields. And at the Lagrangian level, there are no interactions between them. There are interactions among them in each bracket, but not between the different brackets. And that's what one calls factorization. And of course, the non-trivial effects come through external operators. Okay, that's when the interactions come back. So, but let us see what this, so let's reconsider the two-jet current. Right, so I have we had our beautiful two-jet current, which matched onto CV of Q square, and then psi bar n bar WC bar of 0, gamma mu perp, WC dagger psi of n at 0, okay? Let's now do the decoupling transformation, okay? So now I decouple the ultrasoft gluons. Well, notice from here that that's very nice. The product of W times Xi, there's an Sn dagger here which cancels this Sn. So the product W times Xi has the same transformation as Xi itself. That's very nice. Okay, so we just get an Sn from the left. So basically after decoupling, and now, let's see, wonderful. I actually have color here. That's so amazing. Do I have another color? I need 3. Green, wonderful, wonderful, wonderful. Okay. Where am I? Here I am. So now I get the hard matching coefficient, okay? I wanted that already in a color. So the hard matching coefficient in green. This is all the hard physics. Now I want the anticollinear in blue. C bar, N bar, decoupled now. So the 0 really just means no interactions anymore with ultrasoft, okay? W C bar 0. So that's the anticollinear. Gamma mu in white because it's not a field. Now this ultrasoft. So we get from here, we get an Sn bar dagger of 0. And from here we get an Sn of 0. One N bar, not the same, otherwise they would cancel out. If it had the same N, they would cancel. It's like S dagger V prime SV in HQET, okay? So this is the ultrasoft. And believe it or not, the half orange. And that's going to be the collinear. WC0 dagger CN0. That's the collinear. And the key thing is that none of these blocks of fields talk to each other anymore. Inside each color, they interact with the full QCD interactions, gluons with quarks, gluons with gluons, everything there, but no crosstalk between the blocks. So just keep in mind this picture. Anticollinear here is blue. Collinear is here, okay? And ultrasoft in the center, but no crosstalk anymore. When you compute amplitudes, there is a crosstalk, but it's trivial, it's kinematic through momentum conservation. If the collinear carries a certain momentum, the anticollinear carries a certain momentum, the ultrasoft carries a certain momentum. The sum of all momenta is the total momentum, okay? So sometimes this product is in a convolution sense that there might be a delta function telling you that the sum of all momenta needs to add up to the total momentum. And then this means that at the end, these functions will depend on momentum variables, and there might be a convolution over momentum variables at the end of the day. But this is the basis of factorization, basically. So now we have accomplished more, because now so far we had factorized hard from all low energy modes, but the low energy modes still, you remember the picture, always the same picture. The low energy modes, we had Q square, P square, P to the 4 over Q square. The low energy modes depended on, this is green now. This is half blue, half orange, so 2 sectors living here, and no, sorry, well, now I get confused. This is 2 sectors living here, and then the ultrasoft is living down there. Now we have factorized everything from everything. So we have derived an RT equation for the heart function. It's possible now, I won't have the time to do it, to derive RT equations for the collinear functions and for the soft functions separately. And then you can take all objects and move them to a common scale, no matter where the common scale is. You could put the common scale here, you move the heart function down here, you move the collinear functions up here, and you move the ultrasoft function up here, and resum all large logs in the process. That's the idea, okay? So this is a complete factorization, and this ultrasoft function is particularly interesting because this ultrasoft function, you know, here you still have quarks and gluons around and they can interact. The ultrasoft function is just a function involving Wilson lines. And the Wilson lines are, you know, there's a Wilson line in the direction of n, and there is a Wilson line in the direction of n bar, and they come together at this point, point 0, okay? And if you wish, you can now, from these Wilson lines, you can draw as many gluons as you wish. And these gluons, of course, they can now interact through quark loops, gluon loops, in whatever complicated way you want. So once you're in the ultrasoft sector, the Lagrangian is equivalent to QCD. You just start out with a bunch of gluons because that's what the Wilson lines contain. And now you can have a quark loop, more gluons, more quark loops, as complicated as you like, okay? But all ultrasoft. One calls the matrix elements of these collinear objects, collinear or anticollinear, doesn't matter. We call them jet functions. If the jets are the initial state particles in a proton-proton collision, they are also sometimes called beam functions. Beam functions are jet functions, but the word beam means they refer to the initial state, the colliding protons, whereas the jets are typically what you have in the final state, what you measure in your detectors, okay? And the ultrasoft matrix element is called they're called soft functions. Soft functions, ultrasoft functions, normally people just say soft functions. In certain contexts, for instance, in the context of B physics, these soft functions are sometimes called shape functions in a particular context of certain inclusive BDKs, but more generically, we call them soft functions. So at this point, we're almost at the end of the lecture. There's one last point I want to discuss. But before I discuss that, first of all, I already mentioned there is a new homework. And I hear you're still working on the first homework also. That's really great. I admire you because you have a lot to listen to here in the lectures. And if you still find the time in the evenings to work on the homework, wonderful. I think I will send my solutions to the organizers, and at whatever point you think it's good to upload them, you just upload them, okay? And I have attached to today's lecture, if you go online, there's the homework, there's a third file. The third file is another lecture, but not a lecture that can be given on the Blackboard. I already mentioned it yesterday. That's actually an application. So take everything we have discussed from that point of factorizing the current into these 3 blobs. And now the application is the thrust distribution in E plus E minus. It's called an event shape. You have a 2-jet E plus E minus to 2 jets, and you measure certain properties of the 2 jets. And it's just taking everything that's on the board here, including these RT equations, and putting it all together, and at the end of the day, comparing with some data. Okay, so just, you know, after the school, whenever you are on the weekend, whatever, when you have some time, just read this like a novel, okay? Just flip through the pages. You should recognize all the pieces. It's not new material. It's this material, but applied to a real physics problem. And the equations are from a real physics paper, not written by me, written by some other people who did this application, but based on all the formalism we have developed. I want to discuss one last point, and it is this key feature, which is key for the consistency of the whole approach, right? It was key that we don't have higher logs here and higher orders. And also you may wonder why we call this cusp anomalous dimension. Why we call this cusp anomalous dimension is not so difficult to understand. You know that these Wilson lines are integrated out from the point where they start to infinity, okay? So I can, as always, agree that the fields at infinity don't interact, they vanish. I can close this, I get the Wilson loop. You remember this picture, it's again a Wilson loop with a cusp. The cusp is here, right? And I had the same picture in HQET, where the two directions were the velocities. And I mentioned that the fact that there is a cusp with a kink gives rise to ultraviolet divergences, which are controlled by a cusp anomalous dimension. And I gave you even the one loop expression for this cusp anomalous dimension, okay? If I remember correctly, this cusp anomalous dimension as a function of angle was something like CF, I probably get it wrong, but you can look it up. I think it was theta cotangent hyperbolic theta minus 1 at one loop order, where the hyperbolic cosine of theta was v dot v prime. That was the velocity-dependent cusp anomalous dimension, okay? So is there a connection of this velocity-dependent cusp anomalous dimension with my cusp anomalous dimension here? Of course, the answer is yes, okay? In general, if you have a cusp with directions n and n bar, not necessarily light-like, take this for now to be arbitrary vectors. Velocity was special because v square was 1. N is special because n square is 0. Let's assume they're just some vectors, arbitrary vectors. Then the right generalization of this definition is, well, let me use n now, but don't consider them light-like vectors yet. Then the correct formula would be this square root of n squared, n bar squared times n dot n bar. You see, for two velocities, v square is 1, v prime square is 1, so the denominator didn't play a role. And then I get v dot v prime. In general, this is the correct definition. And now you see what the problem is. If we have light-like Wilson lines, n square is 0. So this goes to infinity, okay? Goes to infinity for light-like Wilson lines. And now you can do two things. Either you keep these Wilson lines slightly off the light cone. So you send n squared to 0, but you don't put it quite equal to 0. You keep it very, very, very small. And of course, then this tends to infinity, but it's not infinity. It's just much, much, much bigger than 1. Okay? And in that limit, you can take the limit where cos theta goes to infinity, which means theta goes to infinity. And if theta goes to infinity, the cotangent goes to 1. But you have a theta here. So you say for theta to infinity, you get CF alpha S over pi times theta plus subleading terms. Okay? Now, I don't want to keep n away from the light cone, okay? If I don't want to keep n away from the light cone, there is another element of divergence here because the cusp angle approaches infinity, basically, okay? This is a hyperbolic angle. Of course, in Euclidean space, there are no angles that are infinity, but hyperbolic angles can be arbitrarily large. If you insist on working with light-light vectors like we do in SCET, then in dimensional regularization, this infinity of taking theta to infinity will show up as another 1/epsilon pole. And that's why in the renormalization factor of these Wilson loops, we get double poles and not single poles. Normally, the renormalization of Wilson loop with cusps, you have single poles and the cusp anomalous dimension. If we take the cusp angle to infinity, we get double poles. It's an extra singularity from taking that limit. And in DIMREC, you know what happens. If you have a pole, you get the log mu square that comes with it. So basically, this theta in DIMREC becomes a log of q square over mu square. And the coefficient here is exactly what I call this is called the light-like cusp anomalous dimension. And it's basically exactly so. So the connection is you have the velocity-dependent cusp anomalous dimension, and then you have the light-like cusp anomalous dimension. And the light-like cusp anomalous dimension is the coefficient of the linear term in theta of this object in the limit where theta becomes infinite. That's the connection. And this is an all-order connection. This object is easier to calculate because it's just a number. This is a function. These functions, at one loop it's simple, at two loop, three loop, they become very complicated. This is just a number, which is why this has been computed at for loop order. So, I hope that you also see why it was useful to talk about HQET, I hope, at the end of the day, because there are all these beautiful connections, even though the theories are very, very different, but somehow some of the key tricks and also some of the underlying geometric features are very, very similar in the two theories. And in a way, that's very, very beautiful. So as I said, there is a very large range of applications of SCET. This book by Thomas Becher and al., I think it's still a very good resource if you want to, become a bit more practitioner of the field. I really recommend looking into that book. The first 6 chapters or so you should be able to read without problems now. This is basically the material that we discussed. It has a few more applications in later sections of the book, but the book is also, I don't know, maybe almost 10 years old by now, so there is much more that has been done also that's not covered in that book, but that's more expert material. So that's, sorry, I went a bit over time, but we also have only me as a person to discuss in the discussion session, so we can save some time there. So thanks very much for the excellent questions that you asked so far. It was really a pleasure being here and giving these lectures.